what are the masses? Masses, we took earlier masses to be same, no? Now the masses are different here. So this is C1, C2. With the mass of this, let it be M1, let it be M2. Okay, how to solve this particular problem now? He's asking so many things. Common velocity along line of impact, final velocities along line of impact, impulse of deformation, impulse of maximum potential of deformation, loss in kinetic energy during collision. What is the basic method? We should resolve the initial velocities of that colliding balls along the line of impact. No, just before impact, just after impact, we need that one. So now this should be the theta, and radius is r. So this distance is r. So then from the triangle C1, C2, if I take help of the triangle, sine theta should be r by 2r. So theta is 30 degrees. So here I'll resolve the velocities. One along the line of impact, perpendicular to line of impact. If this is theta, this should be theta. I'll take velocity. So one velocity I'll resolve perpendicular to line of impact. This is before collision. Other will be along the line of impact. Similarly, for this also, a component of velocity perpendicular to line of impact. The other will be parallel to line of impact. Perpendicular I'll show by green color arrow. Can we calculate those velocities? So shall we call that as U1 perpendicular? And this is U1 parallel. This is U2 perpendicular, U2 parallel. This is the just before collision, just before collision. This is the condition. Then how the impulse will act? Along the line of impact. So the direction of impulse we show. So this will be the direction of the impulse. I think now you can manage very easily. This is the impulse that will act. Now we should calculate that U1 perpendicular. So what can this is theta. This is theta. So 4 meter component of that. So U1 perpendicular should be, and this is U1 and this is U2. So U1 is 4 meter per second. So what is U1 perpendicular? Should be equal to let's proceed now. So let's write down all the values. So what is U1 perpendicular? U1 perpendicular should be equal to U1 sine theta. U1 is 4, sine theta 30, 1 by 2, 2 meter per second. U1 parallel should be equal to U1 cos theta. U1 is 4 root 3 by 2, so 2 root 3. Similarly, U2 parallel. Parallel means along the line of impact. U2 parallel should be equal to U2 cos theta. This should be 2 root 3 by 2 root 3. It will be easy if you can resolve. That's all here. It will be easy if you resolve. So 2 1 by 2 theta. So 1 meter per second. Okay, these are the velocities. So now look at that. Quotient of restitution is telling equal to 1 by 3. After collision, what is the one firm thing you can say about after collision? What will be conserve what in what direction. So I'm just asking in what direction you are going to conserve momentum in any direction. But what is the best way of doing this problem? Along line of impact, perpendicular to line of impact. So finally, after collision, we'll go for it. So same set of diagram. After collision, which component of velocities which component of velocities will change, which component of velocities should not change. So the velocities will remain as it is. Shall I write them as V1 perpendicular and this to V2 perpendicular? And now what about the M1, M2 in what direction? You can suggest the values. So I'll assume that this will be V1 parallel and this will be V2 parallel. And what is V1 perpendicular? V1 perpendicular should be equal to U1 perpendicular and V2 perpendicular should be equal to U2 perpendicular. I think the problem has become very simple, you see, and this particular thing is line of impact. What is this dotted line? Line of impact. First, we'll calculate what is V1 V1 parallel, V2 parallel. Because V1 perpendicular already we know it. There's a second sphere. If you can construct this much of diagram, I think problem solved. You are in far better position. So let's apply the conservation of linear momentum along line of impact. So why not along x? Little bit more mathematics along y-axis. So momentum is conserved any direction, but I'll prefer along line of impact. It'll be much easier for us because all the V1 perpendiculars, there are perpendicular components will not change. Only parallel components will be there. Will there be any exchange of velocity? No. Masses are different and E is not equal to 1. So applying conservation of linear momentum, M1 U1 parallel minus M2 U2 parallel. I am going to choose this direction as positive. Should be equal to minus M1 V1 parallel plus M2 V2 parallel. M1 is how much? 2 kg. U1 parallel 2 root 3. M2 4. U2 parallel root 3. This will be 2 kg. V1 parallel. M2 4. V2 parallel. So 4 root 3 and 4 root 3. This will cancel out. So what we are getting is like V1 parallel in fact is equal to how much? 2 V2 parallel. Okay, there's a one equation, keep it here. So let me apply quotient of restitution formula. E is equal to V2 parallel minus of V1 parallel divided by U1 parallel minus U2 parallel. V2 parallel we don't know. Minus of minus, this will be V1 parallel divided by this U1 parallel is 2 root 3 plus U2 parallel is root 3. Value of E we know. Value of E is how much given? 1 by 3. Substituting that 1 by 3 equal to V2 parallel plus V1 parallel V2 parallel plus V1 parallel is equal to root 3. Substitute that V1 parallel equal to 2 V2 parallel 192. So V2 parallel should be equal to root 3, 1 by root 3. We can V1 parallel equal to, so this should be V2 parallel to V2 parallel equal to root 3. So therefore V2 parallel is equal to 1 by root 3. V2 parallel 1 by root 3 means V1 parallel should be equal to 2 by root 3.
Minus 2 by root 3, sir.
Why ma? What happened? Only magnitude.
No, sir, correct, sir, correct. Yes.
Only magnitude I'm finding out. Keep it here. So we have this particular thing. So what is the final velocities now? What about V1, V2? I think I can't magnify less than this. This is the least thing. Now, what is V1? V1 equal to V1 parallel square, V1 perpendicular square. V2 equal to V2 parallel square. So from this, we'll get the final speed or the final velocities along line of impact. Is that okay now? So we have 1 by root 3 and you can see that one. And V1 is 2 by root 2 by root 3 means opposite to that one. There's the meaning of that. And V1 perpendicular already we know. It should be called U1 perpendicular. So using this, I'll get the speed of the colliding objects. I think the maximum part of the problem got over. There's a method of this one. So whenever two-dimensional collision comes, what is very important? Line of impact. Initial velocities, you resolve along line of impact, perpendicular line of impact, and apply conservation of Newton coefficient of restriction along line of impact. The unknowns are obtained. Next, okay, let's come to the collision idea. So what will happen to these colliding objects initially like this? There's a initial, there's a final, what we have. In between what will happen? They'll undergo deform, and at maximum deformation, they'll have common velocity. Will I agree this? At maximum deformation, they'll have common velocity. I want that common velocity. So what is the sequence that will take place now? So they'll undergo deformation. I'm getting into the conceptual part of the problem here. So this is a line of impact. Just I'll give a set of diagrams. It'll be easy for you, this one. One problem if you can manage. So let them ask even here also in 2 dimension you can. No, before collision. So what will happen to the they'll collide like this. Just before collision. Same thing I'm repeating. And they'll start undergoing deformation. No? Like this. This is what, and maximum deformation will occur. And at maximum deformation, rough diagrams it is. Then again reformation begins. Then finally what will happen? They will emerge. Everywhere the concept of that should be retained. Whatever the type of collision, 1 dimension or 2 dimension. This is the initial. This is the final. And here they will have common velocity. So till here is what? Common velocity. How to calculate common velocity? I think we have a very good conclusion here. So let's assume that they'll have common velocity in this direction. And let's try to find out that common velocity. So this particular point I'll call as maximum deformation. So here an impulse will be acting JD and they will have velocity say V1 parallel dash, V2 parallel dash. V1 perpendicular will be there. So I'll show that also. V1, it will not change throughout the problem. So this is what actually the overall U1 perpendicular, U2 perpendicular, U1 parallel, U2 parallel. So that perpendicular components will not change, will remain as it is. Already we have indicated that one. Okay, now let's see that after this. So impulse of reformation will occur. Here the maximum impulse, just call some J or just leave it here or call J that one. Now impulse of reformation will occur, will act. And this impulse of reformation, what it will do? It will make it to acquire velocities, say V2 double dash, V2 parallel double dash, V1 parallel double dash. And finally, it will acquire how much of velocity? V1 parallel, and this is V2 parallel. This is M2, this is M1. Where the maximum deformation will occur here only, where they have common velocity. So for that, what we should do? Apply conservation of linear momentum. Diagram okay? I'll try to shift it down a little bit. Oh, no, not possible. I'm able to show only this much here. How to calculate that common velocity? We should apply, there's a line of impact. So I'll apply conservation of linear momentum. So applying conservation of linear momentum, M1, U1 parallel minus M2, U2 parallel should be equal to M1V M1V. This shall I put minus M1V, M1V. Look at M1 U1 parallel minus M2 U2 parallel. This quantity will become zero, no? LHS. So what is the common velocity? Will be zero. How do you can say? Substitute the values. Looking at these values, no? M1 U1, U1 parallel is how much? 2 root 3. Already I think we have checked it, no? Here. 2 into, okay, we'll do one thing. 2 into 2 root 3, 4 root 3. So therefore the V will be 0. Common velocity will be 0. Is that okay? Fine. After this is asking now the common velocity along line of M 0. Final velocity is a line of M. Got impulse of deformation. How to calculate this? Impulse of deformation. I think from the initial to the third diagram, what all that will act on any one body, that is impulse of deformation. Any formula can you write for this? M1 U1 parallel JD should be equal to, we'll get the impulse of deformation M1 U1 parallel from where to where? You have to pick up from here to here. Is it justified? I think there's something wrong, no? Till V only we should take it, no? And why this negative sign? Nothing to do. V in the direction of this one. So this should be in fact positive only. And this should be not V1, it should be V. So JD should be equal to M1 U1 parallel minus V. Is it okay now? From initial to where they attain common velocity. Maximum deformation is what? Impulse of deformation will act here. What is impulse of reformation? You can pick up anything. So let me take the same M1 only. I need a space. I'll continue below here. Any equation, can we write it here? So M1, M1V. So what shall I write? Plus JR or minus JR? M1V minus JR is equal to minus of M1 V1 parallel. Solve this, you'll get impulse of reformation. From maximum deformation to final situation. Finally, what will happen? The M1 will be moving opposite to that. So plus JR or minus JR. The JR should be with respect to the velocity V. At maximum deformation, the common velocity is what? M1V in the direction. So I'm taking like this here. Solving this, we'll get the JR. After this, impulse of deformation, impulse of reformation. Maximum potential of deformation. Maximum potential of deformation. How to calculate this? The initial kinetic energy here, that should be equal to the difference in kinetic energy at the initial and at the maximum deformation. The difference of that will be converted into maximum deformation energy. So I'll write it, initial kinetic energy is equal to, now what to do here, which energy you are going to take it. What about U1 perpendicular? Will that also will determine, because they remain constant, no? So therefore I'm square plus U2 parallel square. This is the initial kinetic energy. At maximum deformation, what is the kinetic energy? V is 0, no? So therefore, shall I say that what all this initial kinetic energy which was there got converted into, I think this is not some right, K naught, because U1 perpendicular, U2 perpendicular should not come into this picture. So this should be equal to maximum deformation energy. Because finally both the objects, what happen, they're having common velocity 0. So what is the kinetic energy is 0. So what all the kinetic energy due to speed along line of impact, that only got converted into deformation energy. Loss in kinetic energy. What to do for loss in kinetic energy? Initial loss will be delta K should be equal to Ki minus Kf. What is Ki? Here you should include all the perpendicular components. What will happen? They remain constant, no? So I'll straight away, to simplify the problem, I'll directly go for it. M1 U1 parallel square M2 U2 parallel square minus M1 V1 parallel square by 2. Sir, why you didn't brought perpendicular components? Why didn't brought perpendicular components? Why I didn't put perpendicular? Because the perpendicular components, they remain same, no? V2 perpendicular is U2 perpendicular, V1 perpendicular is U1 perpendicular. Only velocities along line of impact, their magnitude and direction will change. So that I am taking LPL. This will be the